In this video, I'm going to demonstrate set comprehensions and quantified expressions. Now, these are concepts in mathematics, but they're also useful in computing, in particular in declarative programming, relational databases, and software specification. So we'll be looking at a model example. So I have some sets and some relations in this example file. And these correspond with what I might have in a database. So I might have a table where these are rows. Or this might also correspond with relations in the Z specification language. Let's walk through what we've got in our example. We have a set of people, and these people are just represented as strings by their names. So I have a string Alice, string Bob, and so on. I have a set of managers, and these are the names of the people who are managers. I have a set of places, and again these are represented as strings. So the places in this model are Birmingham, Coventry, and London. And I have a set of numbers. Now I haven't represented the values in this set. I've represented this using a Python range object, which behaves as if it's a set containing the numbers, in this case 0 to 999. The advantage of using a Python range object here is that I don't have to represent each of those numbers in memory. The range object is a more efficient way of representing a set of a continuous range of numbers. I have three sets of pairs. These are ordered pairs, as you can tell by the round brackets rather than the curly braces. IDs is a set where the ordered pairs, the first item is a number and the second item is a person. And in this case, a pair where I have 111 Alice represents that 111 is the identity or the ID number of the person Alice. I have a set called Is Friends With, and this relates people to people. So this is a relationship between people and people, or a relation. And in this case, a name and a name in a pair indicates that the first person's name is a person who's friends with the second person. I also say that Bob is friends with Alice because these are ordered pairs. So this ordered pair is not the same as this ordered pair. I'm specifying that Alice is friends with Bob and also that Bob is friends with Alice. And finally, I have one more relation here. This is another set of ordered pairs. I have people and places. So in this case, a person's name and the name of a place indicates that this person lives in that place. Let's import this data into the Python shell. The first concept we're going to look at in this video is set comprehensions. The idea of a set comprehension is that I can apply either a transformation or a restriction, or both, on a set of values. And this is useful for computation. It's also useful for specification. The simplest example of a set comprehension, let's suppose I want a set of employees of this company. And an employee is defined as someone who has an ID number. So the company gives ID numbers to its employees. Anyone who has an ID is an employee. Anyone who does not have an ID is not an employee. So I'm going to do a transformation on this set IDs. I'm going to take X. X is going to be my person. And I'm going to take that for the pairs IX in IDs. So this is a set comprehension. The first part defines what is going to go into my set, and the second part defines where it's going to come from. So I have pairs of IX in the set IDs, and then the X, which is the second component of that pair, is what's going to go into my set. And let's call this set employees. If I want to see what employees is, it's a set containing Alice, Eve, Diane, Bob, and Charles, which is what we'd expect. These are in no particular order because it's a set, but that is the same as a set containing Alice, Bob, Charles, Diane, and Eve, as we would expect. I'm going to construct a set of people who are not managers. Now, the simple way for me to do this would be using set operations. I could do people minus managers. This is a set difference, as we saw. And this contains Fred, George, Diane, Bob, and Charles. But I can also achieve this with a set comprehension. So I want the X in people. I have to specify this with the for keyword. So this is what's going into my set, and this is where it's coming from. But I want a restriction on this. I only want to select those people if X is not a manager. So if X is not in the set managers. And this gives me the same set as before, so it's done the same computation, but I can express this as a set comprehension rather than a set difference. These two concepts correspond in declarative programming with a map. So here I'm mapping a pair IX to just the value X, and a filter. So here I'm filtering the set people by this predicate X not in managers. Let's do one more example. So suppose I want to construct the set of people who are friends with Alice. So I'm going to choose those X for XY in is friends with. So I'm choosing the pairs XY in is friends with, but I'm only choosing the X, the first component of that pair, and I only want to select those X where the person they're friends with is Alice. So if Y is equal to Alice. So here I've used both of the ideas. I've used both of the components of a set comprehension. I have a map or a transformation. I've transformed the pair XY into just its first component. And I also have a filter or a restriction. I'm only choosing those pairs where Y is equal to Alice. And this gives me the set of people who are friends with Alice. In the language of relations, this is a relational image. So if I take Alice as my input to the relation, then Bob, Diane, and Eve are the outputs of that relation. And if I use the language of relations, then this computation that I've done here is taking the range of this relation. I've only chosen the values that are the second term in each of these pairs. The next part of this video, I'm going to demonstrate quantifiers. Quantifiers are used to make expressions of statements. So a quantifier gives me a statement which is either true or false. And then those statements refer to how many of something we're talking about, how many of the values in a set the statement we're making applies to. Hence the term quantifier, or quantity for how many. Let's make a statement like all managers are employees. In Python I have an all function, and then what goes into this all function is the statement that I'm making about all of these things. So the statement I want to make is that X is in employees. And then I need to say who I'm making this statement about. This is for X in managers. So this is similar to a set comprehension. I'm choosing what I'm going to have. In this case, I'm taking this expression, X in employees. So I've transformed the values of X. And then here's where those values came from. It's for X in managers. I'm transforming these. But because I'm transforming these into Booleans, this will be true or false for each X. Then here's the statement I'm making about these Booleans. I'm saying all of them will be true. And that's true. Every manager is an employee. Another statement I might want to make is the one that we started with when we were talking about is friends with. When I said Alice is friends with Bob, and Bob is friends with Alice. So I've repeated all of these pairs in both orders. I have to do this because these are ordered pairs, so these are not equal as tuples. But I've set up this relation so that every time person X is friends with person Y is also friends with person X. So I can make that statement. I can say that all of these things are true. YX is friends with. And what am I making this statement about? Where did the X and the Y come from? These are for XY in is friends with. So the statement I'm making here is that for every pair XY in is friends with, yx is also a pair in Is Friends With. And that's true. So the quantifier here is this all function, which is saying that this has to be true for all of the x that we select, or for all of the pairs xy that we select. This former quantified expression here, every manager is an employee, I could have expressed this as a subset relation. I could have said the set of managers is a subset of the set of employees, and that's true. And these are logically equivalent. Everything in the first set is in the second set. Another quantifier, rather than saying all of these things are true, is some of these things are true, or at least one of them. In Python, I have the any function, and then the statement in here will be similar to what I had inside the all expression, except now I'm only saying that this will be true for some value of x, for at least one value of x. So I'm going to make the expression, or the statement, there is some person who is not an employee. So the statement I'm making about x is that x is not in employees. And who am I making this statement about? I'm making it about people. So I need to say where x comes from. This comes for x in people. So this says there is any x in people where x is not in employees. And that's true. There are people who are not in this set of employees. I could have also used a combination of a set comprehension and a quantified expression to construct my set of employees. So let's construct the set of employees using the definition I gave exactly. I said a person is an employee if they have an ID number. If I rephrase that as a quantified expression, if there is a number, at least one number, which is the ID of that person, then that person is an employee. So let's call this employees2 and construct this as a set comprehension. I'll do this over multiple lines because it might get complicated. The employees are those people, but only those if there is any I, which is the ID of that person. So IX is in the set IDs. For I is some number, so there is any number. And that's my statement here. So this part of the expression, this part of the set comprehension is my filter. I only want to choose the x for which this is true. And this being true means that there is some number, at least one number, where IX is in IDs. And if I want to see what is the set employees2, that's the set Eve, Alice, Diane, Bob, Charles, and I can check that employees is equal to employees2. These are equal as sets, they have the same elements, but I've constructed them in a different way. So this is a more complicated way of doing this computation, but it's closer, it's more logically identical to the definition of an employee that I gave. There's often more than one way of doing a computation like this, and in this case this computation is actually less efficient than the one we did previously. If we think about why that is, in this case I have a loop, or this is implemented as a loop, that runs over all of the numbers, and there are 1,000 of those in this model. So this loop over 1,000 numbers is happening each time this loop goes through. Now in principle this doesn't have to be done by a loop, but in practice in Python this will be implemented using a loop. So for each of the x in people, I'm doing 1,000 things. In the previous expression here, I'm not referring to that set of numbers, so it doesn't matter how large that is, I'm just iterating over the elements of IDs, and that will be fewer than 1,000 in this model. So there are far fewer values that I need to loop over in this computation than there are in this computation. And this computation contains a loop within a loop. So I've got my first loop over the set of people, and my second loop over the set of numbers. So in that case, I can multiply the sizes of those loops to work out how many different computations I'm doing. Sometimes I need to use more than one quantifier in an expression. So let's consider the statement, there is somebody who does not have any friends. In this case, there are two quantifiers. The first one is there is somebody, and the second one is not any friends. Both of those refer to how many people we're talking about. So let's begin by saying there is somebody, at least one person. So there is any person who does not have any friends. There are not any people who are friends with X. So let's say that XY is friends with for Y in people. And this says that X does not have any friends. There are no Y in people where XY is friends with. And this is for X in people. So here I have nested quantifiers. I'm saying there is an X in people where this statement is true. And this statement says there is not any person Y where this statement is true. And this evaluates as true. For example, in this model, Fred does not have any friends. My apologies if your name is Fred. Any and all, the two quantifiers that Python gives you, they're not the only two quantifiers that we might want to use in mathematics. So I have another quantifier, there is a unique. For example, I might want to say that there is a unique place that Alice lives in. There is one place that Alice lives in. Or I could say that every person, there is one place that that person lives in. Everybody only lives in one place. Python doesn't give me the there is a unique quantifier, but I've written my own one. That appears in the sets file that I've imported at the top here, so I have access to it here. And if you want to use it yourself, then you'll find it in the Git repository that's linked to at the bottom of this video. If I want to say that there is exactly one place that Alice lives in, then I have a quantifier exactly one. And here's the statement I want to make. There is exactly one place that Alice lives in. So Alice X is in, lives in. This is the statement I'm making about the place X, and X comes from the set of places. And this is true. There is exactly one place that Alice lives in. I might want to specify that for every person, there is exactly one place that that person lives. And I can construct another nested quantifier statement to do that. So for all people, there is exactly one place that the person X lives in. Let's say exactly one place. In this case, instead of saying Alex, I'll say X. So then instead of saying X for my place, I'll say Y. And now this is for X in people. So again, I've used two quantifiers here. I've said this is true for all people. So for all people, this statement should be true. And this says for exactly one place, this statement is true. So for all people, there is exactly one place where that person lives in that place. And this evaluates to true. I'll let you think about how you would write the exactly one quantifier yourself as a function in Python. If you're not sure, then you can see my example. Also in the example code that I've provided, I have a data structure called relation, which allows me to do other computations that you might want to do with relations. One of the differences between my data structure and the data structure that I've used here So that whereas because Python is a dynamically typed language, so although I said the pairs in this relation should be a person and a person, but Python won't enforce that because Python doesn't have static types. So I've got this set of people here, which should represent the type of first item and the type of the second item in this pair. This set of people should represent the type of first item in this pair. This set of places should represent the type of the second item in this pair. I'm not able to specify that with this data structure in Python because these sets are dynamically typed, so they can contain any element that can go in a set in Python. In my data structure, which is called relation, the first input to this constructor method will be the set of pairs. So let's say is friends with, but I also have to specify the source and the target. And that might be useful for type checking in some purposes. So is friends with, the source of this relation, the set that these first values come from, is people, and the target, the set that the second values come from, is also people. And let's change this to be the new value of is friends with. So is friends with is now a relation, and I can see what the values in this relation are. So if I want to do things like find the people who are friends with Alice, that's a relational image. So I have a method on this relation object, the image of, and then when I calculate the image, that's of a set, but this will be a set containing Alice. And this is the same 3 people who are friends with Alice that we found before, but this demonstrates that our calculation was a relational image. I can also find a relation for this lives in. I can write this as a relation using my data structure. So lives in is a relation. The pairs of this set lives in. The source is people, and the target is places. So if I want to find the set of people who live in Coventry, for example, well, in that case, I'm finding an image, but I'm inputting on the right-hand side of this pair, so I need to use an inverse relation. So that would be livesin.inverse in my data structure. So this is now a relation where on the left I have a place and on the right I have a person. So this represents the relation. This place is the home of this person. And I can find a relational image this way. If I want to find the people who live in Coventry, the relational image has to be of a set, so let's put this string in a set. And then this is the set containing Bob and Charles. You'll have noticed that these are frozen sets rather than sets. For some purposes, it's useful to have a frozen set rather than a set. I won't go into details about that. But a frozen set is just a set type in Python. I can also do checks, for example. We said that every person lives in exactly one place. That was this quantified expression here. But this is exactly the definition of what it means for this lives in relation to be a function. Every input has exactly one output. And I can check that here. Lives in is a function. This is true. We also checked that every xy who are friends, yx were also friends. So when Alice is friends with Bob, Bob is also friends with Alice. In the notation of relations, or in terms of relations, this means that is friends with is a symmetric relation. So I can check that is friends with is symmetric. And that's true. Another thing I might want to check is whether a relation is transitive. So is friends with is not a transitive relation, and I can check that this evaluates as false, as it should. What it means for a relation to be transitive means that if x is friends with y, and y is friends with z, then x is friends with z. And that's true in this particular case if x is Alice, y is Bob, and z is Eve, but it's not true in general. I can find examples such as Alice is friends with Eve, and Eve is friends with George, but Alice is not friends with George. Therefore, this is not a transitive relation. I can also do relational composition. So if I want to represent the relation that a person is friends with someone who lives in a place, then that's a composition of these two relations, is friends with and lives in. If I want the pairs where Alice is friends with Eve and Eve lives in Birmingham, therefore Alice is friends with someone who lives in Birmingham, then I can calculate the set of all pairs like this by doing a relational composition. So in this case, the first relation is friends with, and the second relation is lives in, and I've made this multiplication of relation. The result of this is a relation of pairs where Charles is friends with someone who lives in Birmingham, Alice is friends with someone who lives in Coventry, Alice is also friends with someone who lives in Birmingham. So where are the places where Alice's friends live? Well, I can do a relational image here, for example. Let's find the places that Alice's friends live. So this gives me the relation that represents a person has friends living in a place. And then if I find the image of Alice, I should get the set of places where Alice has friends. And that includes Birmingham and Coventry, but it does not include London, because Alice does not have any friends living in London. If you want to find out more about the relation data structure that I've written, or you just want to play around this example more, then you can find this code. This is in a public Git repository, which is linked to at the bottom of this video.